Hello, everybody. It's Professor Ken. Here I am in Haiti, and uh, I'm doing a video to reteach the material from March 24th because, especially in the 8 o'clock class, there were some video problems and computer technology problems. But if I'm making a video for 8 o'clock, maybe everybody can benefit from it. So I'm going to share my screen and go through these slides. And by the end of the slideshow, you guys will be masters at applying derivatives to rates of change. Right. So I'm going to share my screen. I'm also going to turn off my camera so that you're not distracted by my looks. Oh, there it is. Stop video. Perfect. Okay. So slideshow from the current slide. Okay, so today's March 24th, and the function on the right is a graph of position. Is okay. So, and this is a graph that you will find in your book. So we can assume that the x-axis represents time, so we'll call it t, and f of t represents feet, so we'll call it f of t. So just to get oriented with this, we could see that at time t equals 0, we're at 0 feet. After 1 second, we're at 5 feet. After 2 seconds, we're at 10 feet. So you might be able to see a pattern there. So this follows the line y equals 5x. So we can say f of t equals 5t. And when t is equal to 0, that's the beginning of the trip. After every second, we see the object, hold on a second, is 5 feet from the starting point. So that would be the rate of change. So we would say the velocity is 5 feet per second because after every second, the object has moved 5 feet. And velocity is a rate of change of position. So it's also the derivative of position because derivative is a rate of change or a slope. So we say that the velocity function is equal to f prime of t. And let's go up here. So since f of t is 5t, velocity or v of t is 5. So the velocity is constantly 5 feet per second because it's the slope of a line, it doesn't change. All right, here's a new position function. Now we say f of t equals t squared minus 9. And this is how many feet we are from home. An ant is from its home. So at 0 seconds, the poor little ant is 9 feet from home. After 1 second, it's about 8 feet from home. After 2 seconds, it's 5 feet from home. And after 3 seconds, it gets home, but it's still moving. So at 4 seconds, about 7 feet from home. And at 5 seconds, it's about 16 feet from home. That's what this function tells us. So the object, the ant begins 9 feet south of its home. That's why it's negative. After 3 seconds, the object is home and is moving north away from home. After 5 seconds, the object is 16 feet north of home. That's right here. And so we see that at t equals 3, the object is home, but there's still velocity because it's moving north. So the average velocity at t equals 3, well, we can find the average velocity if we use the point at t equals 2 and the point at t equals 4 and use the slope function. So it would be f of 4 minus f of 2 over 4 minus 2, 7 minus negative 5 over 4 minus 2, 7 minus negative 5 is 12, 4 minus 2 is 2, 12 divided by 2 equals 6, so it's 6 feet per second. Let's find the average velocity at 1 second. So that's at this point. So what we'll do is we'll take this point here, and we'll find the slope of that secant line, and that will be the average velocity. So it's going to be f of 2 minus f of 0 over 2 minus 0. It's negative 5 minus negative 9 over 2 minus 0. Negative 5 minus negative 9 is 4. 4 divided by 2 is 2. So right at t equals 1, the average velocity is 2 feet per second. So I have an average velocity helper in Desmos, which is freaking amazing. I mean, darn amazing. Here it is. So what you would need to do in line 1 is type in the function. Then in line 4, you would have to put where you want to find the average velocity. And it does the rest for you, which is what's amazing. It'll find an A value, it'll find which is 1 less than the B value, it'll find a C value, which is 1 more, then it'll do F of C minus F of A over C minus A, and this value right here is your average velocity. So let's find if we have this function, let's find the average velocity at 1. So we're expecting it to be positive and fairly big. I know 1 is right here. Yes, positive and fairly big. So let's let B equal 1. And by the way, this is called Calc 1 velocity formulas. I would ask that you save it into your Desmos account. And when we do that, it changes our A and our C values to what we want them to be. And here's our average velocity, positive 8. Now, the instantaneous velocity, which is the velocity function, is the derivative of the position function. It's right here, and it says if we let B equal 1, the instantaneous velocity is 7. And the derivative at B equals 1 is also 7. So let's try the average velocity now at, let's say 3.5, because it looks to be almost 0 there. I like that one. Let's try 3.5. So it does F of 4.5 minus F of 2.5 over 4.5 minus 2.5, and it gives the average velocity to be 1.75. But what's the instantaneous velocity? 0.75. So that was much closer to 0. So that's how we use this really cool and handy dandy Desmos tool. I hope you learned it. Let's go back to our slides. All right. So if we have F of t equals t squared minus 9, the formula for velocity is the derivative of F of t, which is 2t. The instantaneous velocity at t equals 2 is 4, because you let t equal 2 and you plug it on in. Now, let's take a look at this table. We know velocity is 2t. So if we here's some x values, here's some 2x values, which is the velocity. So we see that the function is increasing by 2 every time the x value increases by 1. So the velocity, which is in feet per second, is increasing by 2 feet per second per every second. So the table to right shows the instantaneous velocities at t values from -5 to +4. Look how the velocities are changing. They're increasing by 2 every second. So the velocity is increasing by 2 feet per second every second, or 2 feet per second per second. That would be called the acceleration, because the rate of change of velocity, or the derivative of velocity, is the acceleration. So even though we are still moving backwards from -5 to 0, we're still speeding up, because the rate at which we're moving backwards is getting smaller and smaller, which means the rate at which we're moving forward is getting bigger and bigger. Let's have a look at t squared minus 9 again. So since the rate of change means the slope, and the slope means the derivative, acceleration is the derivative of velocity. So if we look at this, acceleration is the derivative of velocity. So since the velocity was 2t, the acceleration is derivative of 2t, just 2. So acceleration is always increasing by 2 feet per second every second. So we say it's equal to 2 feet per second per second. A of t equals v prime of t, which is the derivative of velocity, and that's the second derivative of position. So here's an instant where a second derivative has use. Ooh, look at this function. We kind of did this one already. T is greater than 0 because time can't be negative. So what is the average velocity at t equals 4? It's 5 feet per second. That's when we let b equal 4. We see this formula comes out to be 5. What's the instantaneous velocity at t equals 4? Well, here's the velocity function. It's the derivative of f of t. So the derivative of t cubed is 3t squared. The derivative of 8t squared is 16t. The derivative of 20t is 20. And the derivative of 11 is 0. So to find out the derivative at 4, we plug a 4 in here. 4 squared is 16 times 3 is 48. 16 times 4 is 64. 48 minus 64 plus 20 equals 5. So the velocity is 5 feet per second. It's okay if the average velocity does not equal the instantaneous velocity, as long as they're pretty close. Here's our function again. What's the acceleration when t equals 4? Now, it's a beautiful bullseye, but it has nothing to do with t equals 4. It's just beautiful. So velocity, as we saw before, is 3t squared minus 16t plus 20. But the acceleration is going to be the derivative of velocity. In other words, 6t minus 16. So what's the acceleration when t equals 4? Oh, my goodness. 6 times 4, this one, let's see. I wonder who would know what 6 times 4 is. If Schwartz knows 6 times 4, it's 24 minus 16 equals 8. Emily, 6 times 4 equals 24. So it's 8 feet per second. It changes by 8 feet per second every second. So it's 8 feet per second per second. So from t equals 0 to the bullseye, which is at 8/3, the acceleration is negative. Why is it negative? Because the velocity is decreasing. We see that it's big here, a little less here, a little less here. Now it's negative. Then here it's negative, here it's 0, here it's positive. So to the right of this point, it's increasing. So from the bullseye to the right, acceleration is positive because the velocity is increasing. Now, interesting, if we look at the curve, we call this concave down because it can't hold water. If a curve is concave down, the acceleration is negative. If a curve is concave up, the acceleration is positive. So here's problem number 19 from homework. Here's our function. Here's our velocity. And there's our acceleration. So the velocity is equal to 0 when t is equal to 2 and when t is equal to 5. Here's t is equal to 2. We see that it's got a horizontal tangent line. And when t equals 5, it's got a horizontal tangent line. So what's v of 1? Well, here's 1 right here. Let's go up. We see that it's the slope of the tangent line is positive. So we could put a 1 right here. 12. Oh, I'm sorry. This is position. So we see that the velocity is the slope of the graph is hold on. The velocity is 6t squared minus 42. So at t equals 1, the velocity is equal to negative 36 because we put in a 1 squared. 6 times 1 is 6 minus 42. 6 minus 42. I don't think that's the right graph, but 6 minus 42 is negative 36. So the velocity at 1 second is negative 36 feet per second. The acceleration at 1 second is 12 minus 42, or negative 30 feet per second per second. The units are extremely important. And then at 2 seconds, the acceleration is 24 minus 42, or negative 18 feet per second. And the acceleration at 5 seconds, 12 times 5 is 60, minus 42 is positive 18 feet per second Finally, where is the acceleration greater than 0? Well, we would take the velocity, set it equal to 0, and see that it's equals 0 when t is 3.5. So to the right of 3.5, our function is holding water. So that means the acceleration is positive. All right, now we're going to talk about cost. And we discussed this in class, so I'm not going to discuss it in such great detail. But it should make sense to you that the cost for making 1 chair is more per chair than the cost per chair if 500 chairs are made, because we said manufacturing is mass production, And the reason why we do mass production is it makes it cheaper with assembly lines and things like that to produce individual items. So think about buying supplies in bulk, like at Costco and assembly lines. That's why it makes sense that the cost per share is less if we're making 500 shares than if we're only making one. So suppose the cost per chair is modeled by this function right here, negative 0.2 x squared plus 50x plus 100. There it is. So if we let x equal 1, plug that in, we see that it costs $149.80 to make one chair. But to make 20 chairs, we would plug in 20 for x and we get 1,020. Wait a minute, why does it cost? Wouldn't we expect it to be cheaper? Well, not to make 20 chairs, because if we're making 20 chairs for a cost of $1,020, then it only costs $51 per chair. So that would be the average cost per chair. So here's our chair function, our cost function for chairs again. How would we find the function for the cost per chair? This is called the average cost function. So if it costs, the cost to make 80 chairs, we put in 80 for X, is $2,820. So if we divide that by 80, we see the cost for 80 chairs for each chair is $35.25. So the average cost per chair, if 80 chairs are made, is $35.25. So the average cost per chair, if we're making X chairs, is called the average cost function. So we just take the cost and divide it by how many chairs we are making. So in this case, it was the cost of 80 chairs divided by 80. So the average cost function would be the cost of X chairs divided by X chairs would be the average cost of each chair. So here's the cost function. Here's the average cost function. The cost for 80 chairs is $2,820. The average cost for 80, we would just put in an 80 right here to this. We get $35.25. Now, I made a helpful guide for you because I am nice. Okay. Here's the cost functions. So here it is. You would have to type in the cost function. The average cost function is done for you. And you would type in right here how many you're making and the average for each one of how many we're making. And here's a graph that celebrates that. If we turn it off, the average cost function isn't on there. Okay, because it's much smaller. But if you wanted to see it, I would go to my graph settings and I would go from 0, x equals 0 to 250 and y equals 0. And here it is. So we see that the average cost of making one chair continues to go down. Interesting. Helpful. All right. So we talked about the cost function. There's the function for it. We talked about the average cost per chair, which is right there, the average cost function. Now, what's the third type? Well, suppose we're making 80 chairs. The marginal cost would be, what would it cost to make that 81st chair? So it costs $35.25 per chair. But how much would it cost to make that 81st chair? That's called the marginal cost, the next chair up. And the marginal cost is easy. It's only the derivative of the cost function, which might be a little different than what I taught the 8 o'clock class by mistake. So the derivative of the cost function would be negative 0.4x plus 50. Plug in an 80 into that, and we get 18. That means it costs $18 to make that 81st chair. And we would want to find, the reason why this is important is you want to find the smallest amount of the marginal cost, and that's how it tells us how many chairs we should make to maximize our profits. And look, we got another Desmos tool. So here's our cost function. There's our average cost function. Here's our marginal cost function. So the marginal cost for 80 chairs is equal to 18 because that 81st chair would cost $18 to make. Okay. got a few more slides I want to show you with my friend Sir Isaac Newton. Okay, so this is part 2. All right, so what about free fall? When we drop an object, it free falls to the ground. And that's called gravity is the force that causes it. On Earth, the acceleration to gravity can be written in metric or in English. In English, it's negative 32 feet per second. In metrics, it's negative 9.8 meters per second. So if a boy stands above a hole that's 100 feet deep and he throws an apple upward with an initial velocity of 64 feet per second, try and sketch a graph of time versus position. What do we know? We know the initial height is 100. So S0, which is the initial position, is positive 100 because it's 100 per feet above the hole. The initial velocity is upward at 64 feet per second because we know that's what he threw. He threw the apple upward at 64 feet per second. We call that V0. And finally, the acceleration is negative 64 feet per second, although it's negative 32 feet per second. I apologize for that. So our formula for position, and it's always this formula, is negative 1/2 the acceleration times the time squared plus the initial velocity times time plus the initial position. So since acceleration is 64, we say that it's negative 32 t squared. For this particular function, since the initial acceleration was 64, it's negative 32 t squared plus 64t, because the initial velocity was 64, plus 100. And another little tool to help us. So here's our initial position function. Here's the velocity function, which is the derivative of position. Here's the acceleration function, which is the derivative of velocity. Z represents these values at the time. So at 2 seconds, the position is 164. The velocity is 0 because it's at its peak. And the acceleration is negative 32 feet per second. What about, now this is great. So if you have your function, when you're doing your homework, plug it in there. What if we're talking about at 4 seconds? Well, 4 seconds, the position is 100. It's on its way down. We can see that right there. The velocity is negative 64 because it's going downward. That's feet per second. And the acceleration is negative 32 feet per second. We see that doesn't change. Okay, what about at 1 second? When t is at 1 second, the position is 148. That's way up here. The velocity is positive 32 feet per second, and the acceleration is negative 32 feet per second. Why is the acceleration negative? Because it's getting pulled downward. So that's how we use this amazing free fall calculus 1 helpful hint. All right, at what time is the apple at its highest point? What are the position, velocity, and acceleration? Whoops, sorry about that. What are the position, velocity, and acceleration at this point? At what time does the apple hit the ground? What are the position, velocity, and acceleration at that point? And where's the greatest and least velocity? All right, so that graph can tell us all of that. Velocity has magnitude and direction. Speed is just the absolute value of velocity. If velocity is decreasing in the negative direction, then speed is increasing. If velocity is increasing in the positive direction, then speed is increasing. Is speed ever increasing on this graph? Let's take a look. All right, well, let's have a look here. Let's look at our tangent lines. Here's our tangent line is positive. Here it's positive, but it's a little bit less. Here it's 0. Here it's negative, but a little less. Here it's a little more. Here it's a little more. Now, here it's going down, and the velocity is the direction is negative and the velocity is increasing in the negative direction. So actually speed is increasing here because it's getting steeper and steeper. So anywhere where it's getting steeper and steeper, the speed is increasing, even if it's going in the negative direction. All right. Suppose a stone is thrown vertically upward from the edge of a cliff. There's its position function. S of t equals negative 4.9 t squared plus 19.6 t plus 24.5. Determine the velocity of the stone after t seconds. Well, it's just the derivative. So negative 9.8 t plus 19.6. When does the stone reach its highest point? When that velocity is equal to 0. So you would set it equal to 0 and solve it. When is the height of the stone at the highest point? Well, we would graph it and look for it's at its highest point when the velocity is 0. When does the stone strike the ground? When find the t value, which makes when set this equal to 0 and find the t value, or just look at the graph. And with what velocity does the stone strike the ground? And at what intervals is the speed increasing? So let me negative 4.9 t squared. Let's go back to our helpful hint. And it was negative 4.9 t squared plus 19.6 t plus 24.5 plus 19.6 t plus, I believe it was 45, but I'm not positive. Don't quote me on that book. It's 24.5. All right. So we want to know a few things. First of all, at what point, at what time is the velocity 0? Well, the velocity is 0 at its highest point. That's when t is at 2 seconds. What is the highest point? Right here, 44.1 seconds. Let's look at these other questions. Determine the velocity of the stone after t seconds. Okay, we can do that. So the velocity of stone after t seconds is the derivative of position. So it would be negative 9.8 t plus 19.6. There you have it. When does the stone reach its highest point? At 2 seconds. I'm making a video. I'll be right there. What's the... Okay. Okay. I am going to have to stop my video. I did. And stop recording.